So a while ago, I thought it would be a good idea if we had a club mouse. We made UKmarsbot between a few of us. Then of course you come to realize that it's useless without some software. So I made some software for it, Maze Runner, and put that up. And I looked at what I had made and I saw that it was not good. And so well, it had its moments, but they were moments, not minutes. And so, you have to excuse me, I'm a bit not quite with it today. I've got to try and aim that for the microphone. So then I reduced it, simplified it, tried to clarify it, and made a piece of software called Maze Runner Core. And the idea of Maze Runner Core was that I would have no more than was necessary to make a functioning Micromouse on the UKmarsbot platform, but with enough hints, tips, and clues and hooks in it so that if you wanted to extend it to do something better, like running diagonals or running faster or having a smarter solve or whatever, all the bits and pieces were there. Right? And in some places I wrote clues, and in some places I left like empty functions that you could fill in, and that was the thing. And that I like better, and I have now kind of deprecated the original Maze Runner. And if you are starting from anywhere with Marsbot and you want to do C/C++ development, I would suggest that Maze Runner Core is the place to go. But in the end, it's targeted at UKmarsbot, which we know is a versatile but constrained platform. It can only go so fast. It only has, except for those of you strange preverted people who've put Python stuff on it, it only has this lowly 18 mega processor, which has very constrained resources. The rationale behind adding Python and Pico boards and all that, well, there are many reasons why people have done that. But it got me to thinking that really, if you want to extend and develop your skills in building a Micromouse, there would come a point where you need more. And that almost inevitably, that these days almost inevitably means a 32-bit processor at least. And you know, maybe one of these magic multi-core things, maybe an ESP32, maybe have some radio on there, a few IMUs, right? Let's have all of the toys because they are easy to get on cheap boards. And so then I thought about what it would take to put the Maze Runner Core code into a more capable platform, something which could grow into a contest-winning robot. Hence, what I am cutely calling Maze Runner 32. Now, I've forgotten the next slide. Oh, I know. I don't have a 32-bit UKmarsbot board, and it struck me at the time as being slightly pointless putting on all the bells and whistles and all that, because what's the point in having more capable software if you don't then have a platform upon which to run it? And so what I chose to do was to take one of my old mice, Decimus 4, which was retired in about 2016 or 17, and use that as the basis for my extended version of the Maze Runner code. And if I can see over my own shoulder, I took it to APEC and ran it, and this is Maze Runner 32 code running on the Decimus 4 platform. There is no sound. Well, tough, you'll just have to do without. It's really just David Otten in the background explaining more or less what I've just said to you, to the audience. And I'm showing you this partly just to waste a bit of time, and partly to show you that it's not vaporware. You've seen this maze before. There are two principal routes. Nobody took the inviting diagonal. Ooh, has surprises even for me. So the software simply searches to the goal, searches back to the start again, and in a typical APEC maze, that's likely to find you the typically two principal paths that exist in the maze. Because APEC has the search time penalty still, then most robots, and certainly this one, having searched out and searched back, immediately do a fast run on what they perceive to be the shortest route in order to get a time, because usually that's the only time that actually will get you a place, because the penalties accumulate, and so you have to go a lot faster to get a better score on subsequent runs. Then, having done its first speed run, what the software is supposed to do at that point is to carry on and optimize the search a bit more. So it's just had a look down there, which it hadn't been to before, and then it will just go back and forth. When it thinks it's found out everything there is to find out, and you can probably see from this maze that that's not a hard thing to do, it comes back and it starts to do speed runs. There's a touch penalty, but I've already got the best score I'm going to get, so I'll just clean the tyres off, and then we go off and we run it faster and faster. There's further faffing around because the Decimus 4 platform has on it a couple of buttons. It has a little alphanumeric display. Which let you do things like zap the maze or change parameters or run all of the various tests, right? So you have much more than the 16 things that you can do with the switches. So now we've done, this is our third run out. There are two more allowed. And all of these turns, as Derek described, all set up individually and tuned in the couple of weeks preceding the contest. The first speed is the speed that I tuned the turns at. It takes a long time, and I didn't bother to adjust the tunings for the other speeds. And to my great surprise, it managed to do them all even at more speed. That shouldn't have happened, right? Because it is sliding around now, but it's not too apparent. Right, so that's it. That was the last run. It does actually do another one because I didn't stop it fast enough, and it goes off all on its own. So, Maze Runner 32. Bigger, faster, better. He said, as if something should happen. Do it the old-fashioned way. So that's the robot that it was based upon, Decimus 4. No, sorry, that's Orion, right, where we started from. Told you I'm not with it. And that ran the previous Maze Runner core. That ran fine. And these are the constraints that I mentioned before. It's all very well, but up to a point, okay? You can do the diagonals, there is enough memory, there's enough resource, but it'll never be a full performer. It's kind of like a training robot with wheels on, you know, like you had a tricycle or whatever. So then the question is, what are you going to do next? And clearly, I think people want some route to something that'll have more performance. They aspire, one presumes, to being competitive in a contest. Not being afraid that they're going to go home with the whole robot on a bag of bits or whatever. And then there's the question of the half-size contest, okay, which we would like to promote, but not enough people have built robots because that's difficult. But if that has its own constraints, simply storing 1 byte for every cell requires 1K of memory, and if you were still trying to use an 80 mega A328, that's the game over at this point, right? There just isn't enough resource to do that. We want something that can perform well, and I think we've already come across today the idea that being able to do decent simulation would be a good thing. We've seen a couple of examples of telemetry, putting stuff up on the screen. We've seen the idea that if you could have a software simulation on your PC of the search, which we saw, then that would help you. You could test out different algorithms without having to have a huge maze on the floor, without having to take up a lot of space. You can do that in the privacy of your own little house under the stairs or whatever you use for development. And ideally, it would want to be extensible to other hardware. So I have a particular choice of hardware, but I wouldn't want that to be a complete constraint, ideally. There are mice running around with an ESP32 processor, which is a nice processor in many ways, except, as it seems to be so often the case, the ADC is more than a little suspect for accurate work. But it's got a whole bunch of built-in radio and other nice features, 2 cores, you can do multi-processing. Lots of nice bits and pieces. Sorry. That's not right. That's what I want. So we have to make some design choices. Like, what should the hardware be like? Clearly, if you're going to develop new Micromouse software now, it's worth starting off on the premise that it's going to run in a half-size maze. So you start off with the idea that it's a 32 by 32 maze. Why not? You're going to have the resources, and when you explore, you're just using a quarter of the maze. It doesn't know any different after all. And you can fake in the walls for your constrained maze if you wish. Should we use an IMU? Should there be a gyro on there? Should there be an accelerometer? Do I need 3 axes, 6 axes? Do I want to have a compass? No. But IMUs are commonplace. You can get them in nice little breakout boards. They're very useful to have. Why not accommodate one? Mostly you're just going to use the Z-axis gyro, and you can get single-axis gyros. That indeed is what is on the D4 platform. What about communications? Should we use Bluetooth? Should we use BLE? Should we use Wi-Fi? Are those features and capacities in the chipset that you've got? So if you use an NRF 52840 or whatever it is, that has radio on board. The ESP32 has radio on board. But even if you don't have radio on the chipset, it's not hard to plug in, as we've seen, a Bluetooth device and talk back to home base. And if you can talk back to home base, why not make that two-way communication? Now, it's actually verboten to be running your mouse from a PC, but that doesn't mean to say that you can't put two-way communication in, put a little shell program in so you can type in commands to run trials, especially those of us with failing knees who find that it's not so much fun getting up and down, putting the mouse down, run a trial, crash it, pick it up, do it, right? Just sit it down, tell it what to do, and then, in a perfect world, have it send you the telemetry, have it send you the black box data, and then just analyze it on your PC until the battery runs out. So that would be nice. All of this pretty much requires a 32-bit processor, And my preference these days is, and for some time, has been the STM32 family, usually STM32 F4 11s, 13s, or 05s or 7s or something like that. There are others. Duncan has an excellent choice with the F, whatever it was, 03, right. There are lots of them. They're nice, they have very similar capabilities. They don't do these crazy things that some of the other manufacturers, like Microchip, for example, do, where they'll not even bother to put together a full manual. They're a good set of things. One of the disadvantages, I should say, of ESP32 and NRF 52840s is that you end up having to install a whole horrible tool chain, and it's not nice. The STM32 tool chains are very easy to install, so that's a bonus as well. Generally speaking, what I'd like to do is, once you've got all these ideas for your new software and facilities, a mistake people frequently make is they do all this work and then they build a new mouse and then they start on some new software, and now you've got two different things which are new. Two different things that can go wrong, which we all know means there's at least 4 different ways it can all go wrong together, and possibly more than that. So the reason I chose the D4 platform was that had run successfully in the past. I knew it to be a reliable, fast platform, and I can now develop my software on there with some confidence that if things don't go right, I know it's my software, not my hardware. And I would commend this to you. Leapfrog your development so that you only have one set of things to blame. That, generally speaking, tends to be a little more reliable. And so this is Maze Runner 32, which is really D4 with new labels stuck on it, and none of the fluff and muck cleaned off it, I might add. It's had a hard life. In 2015, at a contest at APEC, I dropped it, smashed 2 of the wheels completely into small pieces. You can have a look at it tomorrow, but this white here is tissue paper and super glue as my very own emergency composite structure to put the wheels back together in this 3D jigsaw puzzle in a hotel room, all the while wondering how I was going to explain to David Otten that they've paid me $2,000 and brought me 5,000 miles for nothing. But it worked. I can't take it apart now, it's all glued up. So I might just as well use it for something useful. So who cares, right? I'm here talking to you because I would like you to care, but in general, who's going to use it? What's the audience for these things? Is it something that an experienced builder might want to use as a test bed or as a development? Or maybe my software architecture is different enough that you feel it would be worth changing direction. And I say this not really necessarily by way of, what's the right, I can't think of the right term here, right? It's not a question of, I believe you should do as I do because it's the only way. I'm suggesting to you that I have ways of doing things which might be useful to you, just as you probably have ways of doing things that might be useful to me. But if we don't share enough, right? So I'm happy to put this stuff up, and if you like it, terrific, help me out, add some stuff. If you don't like it, fine. Right? But if you have something to share, really the decent thing is to put it up for everybody to see. So it's not, I don't think it should be just me. I think there are things in there, I hope, for everybody, and by the way, regardless of whether they're using C++ or Arduino or Forth or Basic or Python or whatever, because there are techniques and there are structures which I think have multiple uses. I think, anyway. So what kind of targets have we got? Well, not Python, sorry. Not the RP2040. Maybe some of these other things. And as I've just said, because I forgot what my slide stack looked like, the STM32 is the thing. But why not Python, right? Why not RP2040? Well, I want the best possible performance out of my robot. That's me. Okay, that may not be your goal. Your goal may be something different, or it may be more about learning, or you may not feel up to that. And there are definite advantages in using Python. There are definite advantages in using the RP2040, just as, by the way, you could still run MicroPython on other STM32 processors if you want. The 411, the 413, 405, they'll all take MicroPython. So if you're desperate to do it, you know, the hardware will still let you. But then there's the question of, and the LPC series, the Philips ZXP, they now are ARM core processors, right? Renesas processors, if you're really keen, they've got ARM cores. I checked them out the other day. They don't actually say so, but they're ARM core processors. So then the next thing is, having chosen some hardware, having decided on the processor, what are you going to use to build this thing? What tools are you going to use for the software? And that's an interesting question, and one which really I would like to kind of talk with people about, because the Arduino framework has its benefits, but it's another example of the exact thing Duncan was talking about earlier, where you decide to do an analog read of a pin, and because they don't know what kind of idiotic thing you've done with that pin in the last few milliseconds, they go, just to be safe, I will reconfigure the A to D converter, I will reconfigure the I/O, okay, and by the time it's done all that, you might as well not have read it at all. So I don't think the Arduino framework is a good choice for a performance robot. There's platform I/O and also the IDE, right? I just have a personal problem with the IDE because I think it's rubbish. But there are those who would disagree with me, and we can fight about it on the lawn after. There's platform I/O, which is really just a way of collecting together different frameworks. And if you use that with something like VS Code, you get access to the Arduino framework, you get access to the mbed framework, you get access to the actual ST microelectronics software. Mbed has its benefits, but I would suggest that it's too obscure, right? It hides too many layers of things, and in order to make it work, it's difficult to know what the hell's going on under the hood. If you want to access the hardware, it gets in the way. And so I tend to write stuff straight in raw C++ using, or it will be using the STM32 Cube software, because much as it's a pain in other ways, it is a simple, if you haven't seen it, it's a simple configurator. You pull up the software, you go, I want this pin to be an analog pin, and it will go and set up all the code for you and leave you with the processor ready to do things. And it does beg the question, how complicated does the code need to be to produce a high-performance robot? Right? I didn't bother to bring you video taken from the contest because it's just embarrassing to watch other people go faster than me. But even just to go as fast as Decimus, which we now realize is about only 2/3 as fast as it needs to go these days, right? How complicated does the code have to be to make that happen? I mean, do you have a picture in your head of, knowing what your own code looks like, can you see a path to running that quick? Or are there mysteries that kind of cloud the horizon and say, I don't understand how that could possibly be done? How do you feel about that? Don't have to answer, it's just... Well, go on, tell me. Okay.
So if you've got 10 times more time than somebody else, you could do really simple, crude things, and you won't notice.
That's certainly true to a great extent. So when I put a fan on D5, I remodeled D4, made D5, put a fan on it, and then I started to wonder about what you had to do to take advantage of this downforce, and it turns out the answer is simply turn the speed up. Okay? You can now do exactly what you did before, but faster. That still leaves the question of how do we get to the software that originally ran on D4, and how clever does it have to be? And I think even just today we've probably covered most of the key components that you need to put together to make a high performance mouse. Okay, you need to find a way to get an optimal path, which is not trivial. We've talked about this before. There's a difference between, you know, short paths and fast paths. They're not necessarily the same thing, but that's okay. You need to be able to generate a path that can take advantage of that route. I'm mixing my path and route words up here, sorry. You need to be able to generate something which can actually run this optimal path. So that has to include diagonals regardless of the success of Spira 2. And then you have to control the mouse. Actually, not then, first, long before all that, you have to control the mouse. You have to know that when you say to it, I want you to do 5 meters per second, okay, and not hit stuff, it does. It has to be where you think it's going to be. It has to be where you have told it to be. So that's the thing. And in many respects, that's the hardest thing, okay, because then there are interesting things that happen. You run out of battery headroom, you have to adjust your acceleration for the available current, right? Those things get tricky. So anyway, how complex does it need to be? Well, that kind of depends on your perspective. So this is a class dependency of Maze Runner 32 as it is, not as you will see it one day. You'll be glad to know. But this is the current state. Because I had all of these toys on the robot. I had the IMU, I had the display, I had buttons, I used the wheel encoders for inputs. Okay, all of this stuff, and I saw no reason not to use them. But you may not have all of those things, or you may choose not to have all of those things, and so some of them may go. But at the moment, this is, you know, kind of what we have. We have the mouse itself here. And the mouse is really just a piece of software that controls a robot. Now, that robot could equally be a line follower robot, okay? But this is what turns it into a mouse, effectively. And then the robot has a whole bunch of hardware associated with it that you have to look after. And the mouse doesn't care anything about how all this happens. The mouse has no interest in how the buttons are managed or how the motors are driven or any of those things. It just assumes that it'll work. This is the same as you driving home today or tomorrow. You don't have to know what fantastic advances have been made in adjusting the valve timing and inlet pressures and oxygen mix in your engine. You press the fast pedal and it goes faster, right? Seriously, think about your robot in exactly those terms. I have banged on several times about architecture in the past, and these things that I have banged on about are starting to crystallize into something which I think is much more practical and real that you can look at. And the second to last version that I had, I don't think I've shown this, has these things, right? The mouse needs to have a strategy. How am I going to search? When am I going to give up searching? So, for example, I saw some code recently where a Japanese builder has a timer in to say if I haven't found a route within so many seconds, or I haven't found a better route in so many seconds, I don't have time to mess about, go home and run. If I have done more than X cells, my tires are going to be dirty, slow down a bit whilst I'm searching so that it's safe. These are simple things, right? But they're all part of the strategy. And then your strategy makes use of a planner, and your planner generates a set of instructions for the diagonal run. A dispatcher sends them off, and the robot actually makes all of these things happen. But what's interesting here isn't the profuse use of vague-looking arrows. It's that if you look at it carefully, you can find a division in the diagram. And that division separates the stuff that makes a mouse and the stuff that makes a vehicle, What I called a robot before, now I'm choosing to call a vehicle for reasons which I won't bore you with. It's a vehicle. And if you have that separation and you have a look at the kinds of communication that go on with it, that starts to lead you more easily to the idea that you can have a simulation. So the mouse is hardware independent. That means I can run that software on my PC and I can have a virtual vehicle that I can drive around on the screen. And I just assume that the vehicle behaves properly and does what it's supposed to do. And I can fake up the sensors because I know what the maze map really looks like. Okay, I can know where the mouse is, and I can send out a virtual kind of sensor and say, have you hit a wall, how far away is it? And I can get that information back in my simulation. And a lot of my development then, the strategy, the tricky stuff, the stuff that is hard to do because you've got to deal with your mouse crashing and steering properly, all that can be done in software. You need to communicate between these two things, right? Between the simulated mouse and between the virtual hardware, and that leaves us with a bit of a communication problem. Not one that I have an answer to, but just a few thoughts for you to perhaps consider. And that is clearly the communication needs to be very well defined, so that if I were to write a vehicle simulator, you could write a mouse simulator and hopefully they would communicate, right? And so you would have a universal robot simulator that you could develop line follower or maze solver or whatever software for, and have some confidence that so long as somebody implements a hardware mouse that can do those same things, they will communicate and away you go. This is my goal. This is what I want to do, because I think that's an essential step, in spite of having moaned to somebody earlier about how simulation and reality never mix and how simulation leads to overconfidence and hardware kills that. Nonetheless, there are valuable things that you can do. The most obvious thing really is simple serial messages, maybe sent over Bluetooth if you want to carry that kind of weight around. There are tiny Bluetooth modules. Half-size mouse makes it more tricky, but not impossible. If you're using something like the NRF devices, the ESP32, they have onboard radios and you could connect to the Wi-Fi, or you could do a direct wireless network connection and you could send UDP or TCP packets. If you're not familiar with those, UDP is TCP's unreliable younger brother, and TCP works by telling UDP again and again and again, is that right? No. Is that no? Until it gets it right. So UDP in that sense is a little bit like Bluetooth, right? You poke stuff out, you hope it arrives correctly, and you never really know if it does or it doesn't unless you have layers of protocol on top of it. And you put enough of those layers and you end up with TCP, which is connection oriented. And I'm just suggesting that if you've got space and you can carry Bluetooth, do Bluetooth. If you have a radio capable device, you might want to consider simple UDP. And a side benefit of that is that on a PC, it's quite easy to open a port on the simulator to listen and open a port on the simulated mouse to receive messages, and you have a virtual connection on the same box. So, all in a bit of a rush, that's the current state of Maze Runner 32, which has taken all of my allotted time. We're still running behind. What I intend to do next is to finish the functionality. I've got some refactoring to do, and then strip out a lot of the frippery, okay, a lot of the luxuries that you might not want to put on a mouse, and then put it up for kind of open consumption and debate, and see what people think. So it will become Maze Runner Core's big brother. That's the plan, and hopefully by then I will also have given some more thought to a 32-bit version of UKmarsbot, something that will run Python, and given some more thought to a half-size UKmarsbot, which will be a whole different deal, right? A more complicated processor to deal with the size, but I have in mind a robot driven by two 15mm stepper motors, okay, so to eliminate all of the control issues, well, nearly all of the control issues associated with driving DC motors. You tell it to move 5mm and you just send out steps. And so that's what I have done, that's what I have planned, that's all I have to say. Anybody got any questions or thoughts? Don't start.
I'll start, well, yeah, only three. And they all break out into solutions. So, the one box that perhaps is missing,
Right?
is something we've been doing manually a lot, which is on a real robot, figuring out what the difference is between what the base sensors tell us and what the robot really do.
Well, now there's the thing.
And I don't know what that would look like, but I've got some tests you can only know. Does it move a meter? The robot, you need to take measure out and measure it.
Yeah.
The same thing maybe with acceleration or with sensor calibration. But it feels to me as though some of these robots, especially if you've got an IMU, which is part of the second question, maybe you've got the intelligence on to at least go part of that, because that's quite it's a very yucky process. It's better to give people the tools to help calibrate the robot.
Yeah, I understand that. I have calibration tools. I have auto calibration for sensors that will run up and down and take some averages and work out that kind of thing. You do have to manually intervene. Well, actually, no. I have ideas for how you don't have to manually intervene for all sorts of stuff. So if you're using an IMU, for example, there's a critical thing that you need to know, and that is the gain of the IMU, which won't be what the datasheet says, how many counts before you've done 360. You don't, normally you would do like 10 turns and measure the angle and adjust it, but you've got a post there. Why not just turn around and count how many counts until you see the exact same edge again and again and again and adjust it. And by the way, clockwise and anti-clockwise have different gains, just to be more interesting. So there's a lot of that sort of thing. In the end though, probably at this stage, once you have got those kinds of calibrations done, and the same applies to encoders, and you believe you have an adequate control scheme, CE earlier stuff about feed forward and acceptable PD controllers, then you should be able to have some faith that if you've told the mouse to go to X, it's at X. With the one caveat, which is you should model the slip, but that's much more difficult.
I guess the second part was to do with IMUs, acceleration, gyroscopes. It feels like there is information on the web. There's a lot of black magic going sensitivities between odometry and IMUs
Yes.
and even position sensing. That sounds like a problem. If we wanted more people, it sounds like, I don't know if it's this problem, whether it's a measurement 32 problem or what, but it seems like a problem where we can enable more people to use IMUs more easily in potentially different ways. I don't know how we get over that jump.
If you're just using a gyro,
if
you're just using a gyro, once you've calibrated it up, and so long as you have followed previous advice to use real units and degrees and knot counts and stuff, you simply substitute your encoder difference scaled to degrees with a gyro count scaled to degrees. It's a simple one-for-one swap, and nothing else will change. It'll just work, right? That's why I banged on in the past about the need for this consistency and the use of real world values. If you want to do sensor fusion to try and improve the accuracy of your encoders, there are a few ways to do it, but the biggest motivation for doing it is having low resolution encoders. Now at the moment, MR32 has got high res encoders on, and so an avenue for exploration, possibly after I've poked stuff out, is to say, well, what would happen if I throw away most of that resolution and just pretend it's only got 16 counts per turn or something like that. What do we have to do? And one of the things might be a complementary filter. Kalman filtering is craziness. And people with very fast mice are doing very simple things which you would believe could not possibly work. So Kojima of the turn, he just averages it over the last 100 milliseconds. You'd think this would produce this horrible, unusable lag, right? But he averages that, uses the accelerometer to compensate, and there's no question he goes around quick enough. Okay, so there are simple things that you can do.
Yes, I was talking to what's his name, the guy who did Thunder in the US, and he's got very low resolution cameras, and he uses his accelerometers to things like that. And his first piece of advice was, don't do it.
Yeah, that's right.
It took him ages.
He says on his blog, it's not easy to get right. So a bit like the don't get yourself in a mess in the first place. Try not to do it, but if you have to do it, there are ways to do it. Right, we're just disgustingly late now, but it would be Ian and Deezy.